Okay, so in the previous lecture we discussed about electric field due to an infinitely long straight wire, and that was our first application of Gauss law, right? Now let's see, there are two more applications of Gauss law. So let's move to our next application. The next application is due to a sheet. So let me write here electric field due to a uniformly charged infinite plane sheet, somewhat like the paper sheet, okay, of your notebook. So if you imagine a sheet somewhat like this is our sheet, okay, then we know there are three sections for this sheet. One is behind the sheet, another is on the sheet, and third is in front of the sheet, right? And imagine that there is positive charge on the sheet. We can imagine a positive charge on the sheet over here. Now, if you imagine flux or electric field, it is radially outward. So let's say there is a small section of this sheet due to which electric field is coming out. So we can imagine a Gaussian surface somewhat like this, outward, radially outward, pointing in this direction. And there is another part of this field that will be radially outward in this direction, right? So electric field will exist only in region 1 and region 3. There is no electric field on the sheet, so E2 will be equals to 0. Electric field in region 1 must be equal to electric field in region 3 because it is uniformly charged, right? So we can say that E1 equal to E3 and that is equals to E. So from our basic idea of flux which we have discussed, our total flux phi, that will be equals to E1 plus E3, that our net electric field E1 plus E3 into the area of that part. And E1 plus E3 will give us E plus E, which is twice of E into area, that is flux phi. Now area of that small part. Now phi from Gauss's law, it is nothing but total charge enclosed upon epsilon naught, and that is equals to twice of E into A. Now we know that if it is a charged sheet, then sigma is nothing but the surface charge density, that must be equal to total charge enclosed upon the area of that part. So the charge enclosed by that area will be equals to sigma into A. Let's substitute this in place of Gauss's law. So sigma A upon epsilon naught, that must be equal to twice of E into A. Let's cancel out A with A and we left with E, which is equals to sigma by 2 epsilon naught. Be very careful, we will use this expression in the next chapter. This is electric field, let me write here, electric field due to the sheet, on one side of the sheet. Be very careful, it is on one side. Both the sides it will be sigma by epsilon naught. So one side of the sheet. So this is our second application of Gauss law. You can copy. Because only 3 applications you have, so you have to just remember these Gaussian surfaces, okay? So no other random they will not give you, don't worry about that thing. Let's see the last application of Gauss law. So our last application of Gauss law is electric field. Be very careful, using Gauss law we are just finding field. So electric field due to a uniformly charged thin spherical shell. Okay. So if you imagine a spherical shell here, okay, this is our spherical shell. So in this spherical shell, the charge is present on the outer boundary of the shell. What is a shell? something which is empty inside, like a football. Only the outer covering is there. And on this outer covering, we have positive charge. Okay. And field due to this will be radially outward because it's a positive charge. And let's assume that the radius of this is capital R. If we are looking for electric field at any random point, let's say we are finding the electric field at this point, any point this, which is point P. And this point P is at a distance of small r from the midpoint, the center of this shell. Then we can imagine a Gaussian surface all around like this. Okay. So this Gaussian surface we can imagine. Now we know that flux phi is nothing but E into area, electric field into area of the Gaussian surface. Now what is the area of Gaussian surface in this case? 4 pi r square. Any doubt in this part? Now from Gauss's law, phi is nothing but the charge enclosed by this Gaussian surface upon epsilon naught, and that is equals to E into 4 pi r square. Any doubt? Now here be very careful, though it's a 3D, but here the charges are present only on the outer surface. So sigma will be equals to Q in enclosed upon area. And here where is the charge distributed? So the charge is distributed along the area Q in upon 4 pi capital R square. Be very careful. So if we cross multiply, Q enclosed will be equals to sigma into 4 pi r square. This is our equation 1 and this is our equation 2. Let's substitute equation 2 in equation 1. So Q enclosed will be sigma into 4 pi r square whole divided by epsilon naught, and that will be nothing but E into 4 pi small r square. Let's cancel out both the sides 4 pi. And what we left with is sigma upon epsilon naught into capital R square upon small r square. That's our electric field at that point due to the shell. Any doubt? Now, this is outside the shell. Let's go into on the shell. Second case, yeah. On the shell. Now, on the shell, small r will be equal to capital R. So the electric field straight away we can write it as sigma by epsilon naught because r square and r square gets cancelled. Third case, inside the shell. So it will be 0. The electric field inside the shell will be 0. So why it is 0? Because if we imagine a Gaussian surface inside, there is no charge enclosed by the So no charge enclosed by the Gaussian surface. So hence the electric field will be 0. So I can write Q enclosed will be 0 inside the shell. So here this first chapter gets over. And let's do a few problems based on this thing. Let's see. The question over here says the figure shows 3 charges, 2Q, minus Q and 3Q. 2 charges 2Q and minus Q are enclosed within a surface S. What is the electric flux due to this configuration? Now be very careful, flux is a scalar quantity. So you have to take the negative sign of the charges, right? So that flux we know from Gauss's law is flux phi, that will be equals to the total charge enclosed by the surface upon epsilon naught. Now looking at the diagram, the charge enclosed is 2Q and minus Q. So it will be 2Q upon epsilon naught and minus Q upon epsilon naught. So 2Q minus Q, that is equals to Q upon epsilon naught. We don't have to consider 3Q because it is outside the Gaussian surface. Let's see the next one. Okay, the question over here says an infinite line charge produces a field. So electric field E over here is 9 into 10 to the power 4 Newton per Coulomb, that is our electric field, at a distance r, that is equals to 4 centimeters. So I'm just writing it as 4 into 10 to the power minus 2 meter. Calculate the linear charge density. Now we know that due to a line charge, electric field E is equals to lambda by 2 pi r epsilon naught, right? So we are looking for lambda from this question because r is given and E is given. So lambda over here will be equals to E into 2 pi r epsilon naught. Now majority of the students, they take the value of epsilon naught here and try to simplify. But better way is we can multiply up and down here with 2. Sir, why 2? Let's see. So it becomes E into 4 pi epsilon naught into R by 2. Now exactly. So 1 by 4 pi epsilon naught, that is nothing but 9 into 10 to the power 9. So if you cross multiply, we will get 4 pi epsilon naught is 1 upon 9 into 10 to the power 9. So electric field is 9 into 10 to the power 4, 1 by 4 pi epsilon naught. So let me put here 9 into 10 to the power 9. R over here is 4 into 10 to the power minus 2 whole divided by 2. So let's cancel 9 with 9, and 10 to the power 4 minus 2, 10 to the power 2, and 9 goes up, so 10 to the power minus 7, and 4 by 2 is, one second, let me just write here 7, and 4 by 2 is 2. So that will be our lambda. And what's the unit? Coulomb per meter. So this is our answer for this problem. Yeah. Many of the student as a beginner, they take it as 8.854 into 10 to the power minus 12. Done? Understood? Yeah. Let's see the next one. So question over here says, a cylinder of large length. Large length means you can take it as linear charge, right? Density. And a charge here is Q, that will be equals to 2 into 10 to the power minus weight. Charge of this Coulomb per meter. Now that's not Q. That's what? That's lambda. Because look at the unit. So this is be very careful with the units. Units are telling that this is not charge. Yes, many of the students reading this line, they think that this is our charge, but looking at the unit, it's lambda. Find the electric field at a distance R is equals to 0.2 meter, right? So we know that electric field E is equals to lambda over 2 pi R epsilon naught. Let's multiply up and down with 2, right? Yes. It becomes quite easier. So this becomes our 4 pi epsilon naught into R. Now we know that 1 by 4 pi epsilon naught, that is nothing but 9 into 10 to the power 9. 2 into lambda, that's 2 into 10 to the power minus 8, and over R, which is equals to 0.2, right? Let's remove this point. We get here 10, and cancelling 2 with 2, it will be 18 into that becomes 9 and 1 10 minus, it will become 2. So the correct answer is 1800. So electric field is 1800 Newton per Coulomb. That's our electric field. Understood? Do the next one. So the question over here says a charge of this much Coulomb. So let me just write here Q, that is equals to 17.7 into 10 to the power minus 4 Coulomb, is distributed uniformly over a large sheet. Now area of the sheet is here 200 meters square. Calculate the electric field intensity at a distance. Now R here is 20 centimeters. So 20 into 10 to the power minus 2 meter from it in air, right? So first of all, we know that due to a sheet, the sigma, okay, that is very important because the electric field here E is sigma upon epsilon naught, right? And sigma is nothing but Q by A, right? So Q by area into epsilon naught. Now Q here is nothing but 17.7 into 10 to the power minus 4. Area here is 200 meter square, right? And epsilon naught is 8.854 into 10 to the power minus 12. Now let's cancel out 17.7, that must be 2. 8.854 into 2, I think. Let me just multiply and check. So 8.854 into 2, that's approximately 17.7. So that will straight away cancel out, and here we get 2. So 2 cancels with this, we get 100. So 10 to the power minus 4 whole divided by 10 to the power minus 10, and 10 goes up 10 to the power 6 it will be. That will be our electric field Newton per Coulomb. Any doubt? Understood? We'll move to next one. Okay, so the question over here says a charged particle having a charge. So here Q is nothing but minus 2 into 10 to the power minus 6 Coulomb is placed close to a non-conducting plate having a surface charge density. So sigma over here is 4 into 10 to the power minus 6 Coulomb per meter square. Find the force of attraction. Now we know that force F is equals to Q into E. Now E is nothing but sigma by 2 epsilon naught one side, because it's placed on one side, right? So sigma upon 2 epsilon naught. Now let's put the values. So Q here is minus 2. We'll ignore the negative sign. 2 into 10 to the power minus 6. Sigma is 4 into 10 to the power minus 6 whole divided by 2 epsilon naught, which is 2 into 8.85485 into 10 to the power minus 12. Let's simplify it. So 2 cancels with 2. We left with 4 upon 8.85 into 10 to the power. Now minus 6 and minus 6 minus 12, that cancels out. And when you divide this, you get 0.45 Newton. That's correct. We move to the next one. Here. So the question over here says a particle of mass 9 into 10 to the power minus 5 g. So let me just write here, mass is in grams. So let's convert it into kgs. So 10 to the power minus 8 it will become. So minus 8 kgs is kept over a large horizontal sheet of charge density. So sigma is given here as 5 into 10 to the power minus 5 Coulomb per meter square. What charge? So they are asking Q. So that if it is released, it does not fall. So if something is falling, it is falling because of gravity. So simply force must be equal to mg. And force is nothing but Q into E, that is mg. And E for a sheet is sigma by 2 epsilon naught. That is equal to mg. Correct? So here Q will be equals to mg into 2 epsilon naught over sigma. So let's substitute the values. M is nothing but Q will be equal to M is nothing but 9 into 10 to the power minus 8. G is 9.8 acceleration due to gravity. 2 into 8.854 into 10 to the power minus 12. You can take it as 10, doesn't make any difference. Whole divided by sigma, which is 5 into 10 to the power minus 5. And if you simplify this, okay, I'll just directly write the value. It will be nearly 3.12 into 10 to the power minus 13 Coulomb. That's our correct answer. Yeah, fine it is. Okay, we'll move to next one. Says 2 large metal plates. So let's draw here 2 large metal plates, each of area 1 meter square. So this is 1 meter square and this is also 1 meter square. Are placed facing each other at a distance of 10 centimeter apart. So the separation is 10 centimeter and carry equal and opposite charges. So if this is positive, this will be negative. If the electric field between the plates is 100 Newton per Coulomb, so electric field E is 100 Newton per Coulomb. Find the charge on each plate. Okay, fine. So if it is positive, the field will be outward, and if it is negative, the field will be inward. So you can see that electric field due to the first plate will be E1 and E2, and both are pointing in the same direction. So net field will be E1 plus E2. And E1 is nothing but sigma by 2 epsilon naught, we learnt, plus sigma by 2 epsilon naught. So the total field will be sigma by epsilon naught, right? That is our electric field. Now sigma here will be a charge upon area. So we have to find charge, right? Yeah. So E will be equals to Q by area into epsilon naught. Let's cross multiply. So Q will be equals to epsilon naught A into E. Epsilon naught 8.854 into 10 to the power minus 12. Area is 1. So we can ignore this. E, electric field is 100. So straight away it is 8.854 into 10 to the power minus 10 Coulomb. Any doubt? We'll move to next one. Okay. So here the first chapter overs. Okay.